Good day everybody. Today I shall be discussing about silicon controlled rectifiers, which is shortly known as SCRs. So these silicon controlled rectifiers are very widely used in industries, and it is available in different power ratings, and particularly it is used in power and control circuits. It is an electronic device which uses the PN junctions. Unlike a PN junction diode, it has 4 junctions. So let us look at the diagram here. First, it is a 3-terminal device. The symbol is like that of a diode. This is a symbol, but it has a third input known as the gate input. Whereas, so these two are anode and cathode. As the symbol indicates, it acts like a diode. That means it acts almost like a short circuit between the anode and cathode when the gate is applied a positive pulse, when a positive pulse is applied to the gate. On the other hand, when the gate is open and a voltage is applied here, it acts like an open circuit. Hence, through a small voltage applied at the gate, a circuit which is connected between the anode and cathode can be controlled. That means a switch, it is like a switch. So the SCR acts like a switch, and this can be closed by applying a small positive pulse at the gate. And once the positive pulse is applied, it acts like a short circuit, and even if the positive pulse is removed, it remains like a short circuit. That means it can be used as a switch, which can be controlled by a small gate potential. So that's how an SCR functions, and the circuit symbol for an SCR is as given here. And the construction is as given here. It is a junction device with 3 junctions basically. So this is one junction, it's a PN junction, this is a second junction, this is an NP junction, whereas the third one is a PN junction again. And here this is gate, this is the anode, whereas this is the cathode. And the gate is this terminal. So it is a PN device. Now let us see how this PN device works like an SCR, works as an SCR, silicon controlled rectifier. Now this PN device can be cut like this, as shown here. If you cut this device over here, please note that it is a PNP transistor and this is an NPN transistor, where the base for the PNP transistor, N is the base and P is the collector, where this is the emitter. And now this N of this PNP transistor is connected in a way to this NPN transistor, or it is where the N is shorted to the N of this NPN transistor here, and this P device of a PNP transistor is connected to the base P material of this NPN transistor. It can be viewed like this, and it is convenient to view like this for understanding the operation of the circuit, operation of the device. So this device can be now represented in this fashion, where we have a PNP transistor. This is PNP transistor, and an NPN transistor. This is an NPN transistor, and the base of the PNP transistor is connected to the collector of the NPN transistor, and similarly the collector of the PNP transistor is connected to the base of the NPN transistor. And this is the anode, this is the cathode, and this is the gate. So please note that it is a PNP device, and here it is an NPN device. Now this base is connected to the collector, and this collector is connected to the base of this transistor. Let us call this transistor as Q2 and this transistor as Q1. Now since this N region over here is connected to the N region of Q2, this connection is valid. So this can be represented in this kind of circuit form. So this is a 3-terminal device now. Now let us see, with the help of this diagram, we shall see how this circuit works. Now when the gate is open, for instance, when the gate is open, if you apply some potential between the anode and the cathode, what happens? Please note that when the gate is open here, this PN junction is not forward biased, and since this is not forward biased, there is no base current that flows through this, and as a result there is no collector current that flows, except for the reverse saturation current that flows in this direction, IC naught. Or in this particular case, this collector current 2 is equal to the reverse saturation current IC naught, which flows from the base of this transistor. And the order of IC naught in the case of a silicon material is very small, which is of the order of a few nanoamperes. Hence, so this current is negligibly small, and it doesn't allow any current to flow in this direction, and it doesn't turn on the transistor and no current flows through this. Hence, except for this small current IC naught, there is no other current which flows through this device. As a result, so this device acts like a high impedance and no current flows. Typically, the impedance is of the order of hundreds of kilo ohms. R of is of the order of hundreds of kilo ohms when the gate is open. Now, if a positive potential is applied to the gate, say at time t is equal to t1, initially it was 0, and now some positive potential is applied to the gate such that it makes this PN junction forward biased. That means this potential is larger than about for the cut-in voltage of the transistor, that is of the order of 0.6 volts. Now when in that situation, now base current flows into this transistor, this IB2 into transistor Q2, IB2 flows, and this current results in a collector current. So beta 2 times this IB2 would be the collector current, which is definitely much larger than this IB2, and this current contributes for the base current now for this transistor Q1. Therefore, now beta times that current would be flowing through this transistor now, because this current biases this transistor and it makes the PN junction potential forward biased, and since this current is coming now, the transistor is on, therefore the collector current, large amount of collector current flows, and this large amount of collector current now adds to this gate current which is supplied by this positive pulse, and in turn a large amount of collector current flows, and that is equal to the base current now, and again beta times that would be the collector current here, and that is equal to the base current, again further beta times that flows through this, and again beta times that flows through this, and this way the current regenerates itself, and very soon, within a very short time, you will find that a huge amount of current flows in this circuit. Hence, so this circuit almost acts like a short circuit. For a finite voltage V, a large amount of current flows through this, and as a result, now this one acts like a switch. It turns on, and in case there is a load resistance across within the circuit, in series within the circuit, and this one acts like a switch, and it allows current to flow through, and except for a small amount of current here, most of this V appears across the resistance, and hence the circuit gets switched on and the voltage appears across the resistance R. And during on condition, the resistance that is typically offered is of the order of 0.01 or 0.1 ohms, so which is very small. Hence it is, for all practical purposes, it is like a short circuit, and the circuit now acts like this, with the SCR acting like a switch. The circuit is like this, and this is closed by a small gate potential of this type, a positive potential of this type when applied to the gate, so it switches on. So R off is this, and R on is of this order. Now, if the gate potential is brought down to 0 at t equal to t2, at time t2, if the gate potential is brought down to 0, then what happens? If this is brought down to 0 now, naturally no further gate current flows into the circuit. But what happens to the circuit? The circuit is already on. Because of this positive potential, it generated some base current, and which in turn generated some collector current here, and that is supplying now to this transistor. And since this supply is still on, even if this is cut off, this supply is still on, and that regenerates this again. Therefore, this circuit remains on. So initially, to start with, it was off, and it is turned on here. And once this is turned on, even if the positive potential at the gate is removed, it still remains on. Hence, a small triggering pulse is sufficient at the gate to trigger the switch. So that's how the SCR works. Now, once it is on, the SCR is on, how to turn it off? So by turning off can be done by two means, by two ways. So this can be done by either turning off the current, turning off the circuit current, or it can be turned off by applying a negative potential at the gate. Now, if this is turned on, that means if the circuit is broken somehow, or the current flowing through the SCR is made to go down to 0, then when there is no potential applied here, that means when it is at ground potential, and if the current is broken, then what happens is there is a discontinuity in the current that takes place. The moment it is broken, there is no collector current, therefore there is no base current here, therefore there is no collector current except for IC naught, and that is not sufficient to turn on this Q1. Hence, this goes off. And when this goes off, even if this is connected, in the absence of a positive potential here, so it acts like what we had before t equal to T1. That means it is like a relaxed system, and when no potential is applied, that means initially when the current is 0, when no potential is applied, because of no current, no base current and no collector current except for IC naught, so this one remains off, and it offers a high input impedance, high impedance, which is of the order of hundreds of kilo ohms. Hence, if the current is broken, when the potential is 0, gate potential is 0, the SCR goes off. So this is how, by breaking of the current flowing through the SCR can be turned off. Similarly, when a negative potential is applied to the gate, that means to the gate with respect to the emitter of Q2, if a negative potential is applied, then initially say it is an on condition, like it is here now. Let me draw it separately. So this is the SCR, this is the PNP device, this is the gate, and this is Q2, which is an NPN transistor. So this is the anode, this is the cathode, and this is the gate. Now the situation is when T is here. So during this condition it was on, and now it is on. Somehow it is turned off by breaking the current, or okay, that is a different one that I have discussed already. Now let us see a situation. It is already turned on by this positive potential, and we are now at in between T2 and T3. Now at T3, if you apply a negative potential like this to the gate, that means between the gate and the cathode, because if I show it as ground, if we apply a negative potential here, and when the SCR is in conduction, is an on state, what happens is this negative potential which is applied between the ground and between the gate and emitter of Q2 turns off this transistor Q2. And when the transistor is turned off, naturally, so no base current flows. At T3, initially there was current which was flowing between the collector current IC1 from transistor Q1 was flowing, and that was flowing into the base of Q2. But now, because of this negative potential applied here, so this current will now get routed to the negative source, and this junction being now reverse biased, no base current flows. And when no base current flows, the collector current becomes 0 except for IC naught. And when the collector current drops down to 0 here, almost 0, this base current is equal to 0, drops down to 0. Therefore, this collector current now drops down to 0. And as a result, both Q1 and Q2 goes off. That means the SCR goes into off condition. Therefore, here the SCR is turned off. Now, even if the potential is removed and it is again made to be 0, the SCR still remains in the off condition. So SCR remains in the off condition until another positive pulse is applied. So this is how an SCR works as a switch, to switch the voltage across the load or some circuit. Now, please note that for any device, particularly semiconductor electronic devices, which are made of PN junctions, when the potential is applied across them up to certain limit, it acts like an open circuit, and when it is initially turned off and when there is no gate pulse applied or no positive voltage applied to the gate. Please note that if we increase this potential now, the voltage that is applied between the anode and cathode, what happens is the junction reverse potential across the junctions, these PN junctions which are present here, this voltage is applied, gets divided between the various PN junctions over here. Now if the potential is increased, a point when this potential is increased, the potential across each junction reaches a breakdown potential where these PN junctions break down. Please refer back to the PN junction diode, discussion on the PN junction diode. Beyond certain limit in the reverse potential, there is avalanche breakdown which takes place because the potential difference across the junction forces the bonded electrons to get out of the covalent bonds, and the bonds are broken and the electrons become free electrons and the conduction takes place. Therefore, the SCR breaks down beyond certain positive potential. And that's what happens even when this potential is reverse biased, when the cathode is forward biased and the anode is reverse biased, the situation is similar and the breakdown occurs. Now let us look at the characteristics of an SCR, silicon controlled rectifier. The VI characteristics of an SCR are as shown here. Now when the gate potential is 0, this is the voltage that is applied and this is the current. So let's call it as anode current. Now when a positive voltage is applied, when the gate current is 0, negligibly small amount of current flows through the device, and this current is such that this current is equivalent to a current which is offered by a resistance which is of the order of hundreds of kilo ohms. And this is what happens until a breakdown potential is reached. And when a breakdown potential is reached, so there is a sudden increase in the current and the voltage applied across the diode goes down if there is a series resistance, and the characteristics is like this. At this point, it breaks down. The device breaks down and current increases. If there is a series resistance across the between the SCR and the supply, so the voltage gets dropped across the series resistance, and as a result the voltage across the SCR drops and current increases. So this is what is the case when the Ig is equal to 0. Now if Ig is not 0, So naturally, with a certain positive potential, with a small amount of positive potential, the characteristics is like this. With a small amount of positive potential itself, the device conducts, and both the transistors, the equivalent transistors, are turned on, and this is what the characteristics that are obtained. This is for, let us say, Ig is equal to Ig1. If this current is the gate current is slightly appreciable, which is resulted when the base to emitter junction potential is of the order of 0.7 volts, then what happens is, with a very small amount of voltage between the anode and cathode itself, the device gets turned on, and this is the characteristics that is resulted. This is at Ig2, Ig is equal to Ig2. Now in the reverse direction, so it acts like a reverse biased, so PN diode, an avalanche breakdown occurs at certain breakdown potential, and the reverse current increases. So this is the reverse breakdown voltage. So this is the reverse breakdown voltage on the voltage scale. Now this voltage is the forward breakdown voltage. Forward breakdown voltage. So which is represented as V by BR, and VBR, the breakdown potential occurs under different situations of the gate. When the gate is open, the breakdown potential that occurs is known as VBRO. When the gate is short circuited to the cathode, then it is VBRS. And sometimes in the circuit, to limit the gate current, so a resistance can be connected between cathode and the gate, in which case it can be written as VBRR. So these voltages are different. Now, under different gate currents, the characteristics are as follows, as I have mentioned. Please note that, so this current is known as the current at this point, that means this horizontal point is known as on the horizontal line is known as the holding current, IH. That means immediately after the breakdown potential, this is the current that at which the device voltage falls down from the breakdown potential to this potential. So that current is known as the holding current, and this is the holding current when the gate current is 0, and this is the holding current when the gate current is Ig1, and here the holding current is not properly defined. At this current, the holding current is definitely over a very short range, and please note that the holding current is the current which is shown here as the current that is corresponding to the current at which this voltage drops, but the holding current is defined as the current when the device current is brought below this current, it changes from this on state to this off state. From here to, from between this point to this point, here the device is off when the gate current is 0, and the device is off from this voltage to this voltage when Ig is equal to Ig1, and similarly for Ig2 it is up to this. Now IH is the minimum current, so that flows through the device when it breaks down. Now if the device current is brought below this IH, the device jumps from on state back to the off state. That means through a gate pulse or through a breakdown potential, by applying a potential which is more than the gate breakdown potential, if you make the device on, then if you want to turn off the device, then you should see that the current that is flowing through the gate current goes below the holding current IH. If you break the current completely and make it 0, so naturally it is going to be off. But it's not necessary that you have to make it 0, but if you make it less than this holding current, so then it goes into off state, because this is almost, because this point is almost, it is this kind of a point. So it has, the current is almost constant here as the voltage is varied. So once you go below this holding current, you find that the operating point goes on to this side. So naturally, because when you reduce the current, the operating point goes like this, and once you go below the holding current, the operating point comes onto this side. And on this side means the transistors Q1 and Q2 are off, except for that IC naught. And whatever is the current that is resulting because of IC naught, is that corresponding current is the holding current IH. So this is how the device works, and this is what the the VI characteristics of the device is. Please note that this is known as the blocking region in the forward direction, and this is the blocking region in the reverse direction. Now, what about the switching times? When the device is switched on, for the regenerative action to take place, and the switch to get closed, what is the amount of time that is taken? The time that is taken for the switch to be turned on is very small, which is of the order of microseconds, and it is of the order of 10 microseconds in the case of low power circuits, and it is of the order of 100 microseconds in the case of high power circuits. That means when you operate the device in high power, the switching takes longer time, because the current has to go up from a small voltage to a high voltage, a small ampere rating to a 0 amperes to a high range. And the total ampere, the specifications of the device are as follows. So IH the holding current, the breakdown potential, and the maximum current that can flow through the device. And VBR, the breakdown potential, means this is the maximum voltage that can be applied across the device. This is the maximum voltage that can be applied across the device without turning on the circuit. There is a maximum current, so that can be passed through this device without harming the device. So that current is known as the maximum current. And the maximum voltage typically for power devices is of the order of kilovolts. A typical value is 1800 volts. And this maximum current can go to a whopping rating of 2000 amperes. That is the order of the current it can sustain, the device can sustain. The holding current is very small, which is of the order of a fraction of a milliampere. For zero gate potential and even for appreciable gate currents, it is a fraction of a milliampere, but it is of the order of microamperes. And please note that with this kind of voltage and with this kind of maximum current that can flow through this device, it can be operated in circuits handling powers which are of the order of hundreds of which is of the order of 10 megawatts. Therefore, this device can be used in high power circuits. I repeat, this device can be used as a switch to switch on the power to a high power circuit. Here I am showing a DC voltage, but it can be an alternating voltage source also, and this can be applied to the load through a small gate potential. By applying a small gate potential, you can control this and make use of it as a switch. With mechanical switches, we have difficulty. The difficulty associated with mechanical switches is you have to manually or through some, again, a big control circuit, you have to, or a pneumatic or hydraulic control circuit, you have to turn off. And particularly when thousands of amperes of current is flowing through the circuit, if you want to turn off, break the potential, it's very difficult. You have to take a lot of care. Whereas a small SCR can be used to switch such huge powers, and that can be done by applying a small positive or negative potential at the gate. That is the advantage with SCR. So as I have already mentioned, so it can be applied in power circuits as a control of power circuits, or basically switch gears. It can be used typically in control systems which are non-power applications, and it can be used in regulated power supplies, we can see that it switches on a resistance across some circuit the moment the voltage goes beyond certain value. The moment a voltage goes beyond certain value, you can see that the gate is turned on, the device is turned on by a positive pulse to the gate, and it switches on some other circuit, and the current can be switched into an alternative path. So it can be used in battery chargers. It can be used in protective circuits. That can naturally, you can see that it gets shorted, the potential across a device gets shorted the moment some other voltage goes beyond a certain limit. It can be used in heater controls or in general control systems, as I have mentioned. And there are many other applications. And this SCR is also known as a thyristor. It's a PNPN diode, PNPN device. It's known as silicon controlled rectifier, in short as SCR, and it is also known as a thyristor.